Okay, so welcome to Math 355, Section 2. So this is Lecture 12. And so actually, I guess I should probably go to the opening screen. So in Section 1 today, we did the theory. So we concentrated on what is a field. We did some examples of fields. And then there were some problems in fields that we did not really go to in full detail that I've left for them to think about, or maybe we'll talk about over here. There are some things we can do independent of that theory lecture. And then on Thursday, we'll do the theory lecture here and we'll switch. What I want to do is I want to use today's class productively to talk about how you can use computers to help you gain intuition by just gathering lots of data and building conjectures, or just doing some calculations and saving yourself tremendous amounts of time. This is the 21st century. There is a small split in math departments as to should programming be required to graduate as a math major. I hate the word required because as soon as you say required, everyone has to do it. I strongly urge you to know how to write programs. I strongly urge you to take a stats class. Just like I urge you to take humanities classes. You should know how to write well in the 21st century. I will be teaching some writing intensive math classes hopefully next year where you will actually be writing that will be read by people other than myself. Okay, so what I want to do today is talk about how to do some simple coding for stuff like this. I am going to use Mathematica because that's what I used when I was in college. This is very similar to why do we use the QWERTY keyboard? Because your adults used the QWERTY keyboard when they were young, and so you're going to use it, and your children will use it until we get to the point where we're no longer actually having keyboards and we're just moving hands in space or just completely talking to the computers, which a lot of us now do because of the voice software. So Mathematica is great. It has a lot of wonderful predefined functions. And then you can use those to make more involved user-defined functions. So a lot of things are already there. It has wonderful graphing capabilities. You can write code in it. It has a lot of great things. It sometimes reminds me of the singing horse. What is amazing is not that the horse sings well, but that the horse sings at all. If you have to do serious number crunching, Mathematica is not necessarily the best one to use, but for a lot of what we're doing, it already has all these number theory, abstract algebra functions predefined, so you don't have to create them. It's not hard if you know how to write code to write a program to construct the GCD. However, Mathematica already has that predefined. That's a really nice feature. All right, so let me start off with today. So there's just some general links on my webpage. You can get to some links about Mathematica, including some sample templates and some videos where I go through and just show how to do a bunch of things in it. One of the things you have to be a little bit careful about is as the software changes, sometimes commands that worked before no longer work in later ones. So I know Mathematica fixed a couple of things from when it was really early when I was extremely young. It's now done a better way. But a lot of us old timers were used to programming it in certain ways. Also, some functions are more powerful than they used to be. They have more options and things you can do. So you always want to look, and I'll show you how to look for stuff like this. I've got a bunch of sample codes over here. So if you want to try your hand at some problems, you can actually go through and there hopefully will be some comments. All right. So before getting to the coding, I want to talk a little bit about some motivation for chapter 5. We're going to be looking at fields, field extensions. One of the big goals is to try to solve polynomial equations. Some polynomial equations are very simple to solve. If I give you ax plus b equals 0, I am assuming everybody can solve and find that x is equal to negative b over a. What's the one thing I have to be careful about? We're mathematicians. What do I have to be careful about? Yeah, a is 0. So I might say, look, I want to solve ax plus b. I want to solve a linear equation. I don't want a to be 0 because then it's not a linear equation. Or is it a linear equation with 0 leading term? I like my leading term to be non-zero. If I give you a quadratic, we have the quadratic formula. And so does anybody know how to prove the quadratic formula? So one is complete the square. And what I want to do is I want to talk about a natural way to get to that. And part of this is what you do is you do things in stages. So we know how to solve a linear equation. What's the simplest quadratic? If I give you ax squared plus c equals 0, then this is just x squared equals negative c over a. Thus, x equals plus or minus the square root of negative c over a. So if we have a quadratic with no linear term, we know how to solve that. So then if I give you something in the form ax squared plus bx plus c equals 0, I want to write this as maybe alpha u plus squared plus gamma, I'm sorry, right, equals 0, with u some nice function of x. If I can do that, I know how to solve something in the form alpha u squared plus gamma equals 0. So this is what's suggesting trying to make this a square. So I want to write this as, a x squared plus b over ax plus c equals 0. And it would be wonderful if what I had inside the parenthesis was a square. And so what I'm going to do is I'm going to add 0. And so I'm going to add b squared over how many a squareds? 4, excellent. And I'm going to subtract off b squared over 4a squared. You can look and see if I have chalk. Let me just quickly pause while we look for chalk for. Okay, so we've basically added in such a way that now we can write this as a x plus b over 2a squared minus b squared over 4a squared plus c equals 0. And this is over the form, a x plus b over 2a squared minus b squared over 4a plus c equals 0. And so this is then a x plus b over 2a squared plus, and then how do I want to write this? I can write this as negative b squared minus 4ac parentheses like this, all over 4a. So x plus b over 2a equals plus or minus the square root. I'm going to take the negative of this divided by a, so it's going to be b squared minus 4ac all over 4a squared, which is plus or minus the square root of b squared minus 4ac all over 2a. So x is negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. And so we can see how we get our solution. Another way we could have looked at it is we can solve x squared plus c equals 0. We can solve ax squared plus c equals 0. We can solve ax plus h squared plus c equals 0. We slowly make it more and more complicated. And then the hard one is a x squared plus bx plus c equals 0. Does anybody remember what you call a polynomial written in this form? I have the advantage that I have kids who've gone through algebra in high school somewhat recently. This is the vertex form. So anyways, the way we solve the quadratic is we start off with a simple quadratic that we know how to solve, and then we show that a more complicated quadratic can be reduced to that form. So the hope is that we can do that for more complicated things. What if we take a cubic? What if we take a quintic? And so on and so on and so on. And that's where things get interesting. So it turns out that if I give you any polynomial of degree at most 4, I can explicitly write down the roots of the polynomial in terms of the coefficients of the polynomial. But once you get to degree 5 and higher, you can't write down the roots of a general polynomial in terms of the coefficients. That doesn't mean that the coefficients don't uniquely determine the roots. It just means we can't write them down in a simple closed form expression involving, sums, products, quotients, roots. Can't do it. So the proof of this is typically done in Galois theory, which is the next natural class to take after this. An absolutely beautiful subject as to why can't you do degree 5? What magical thing stops when you go, we can do degree 3, we can do degree 4, we can't do degree 5? How many of you have seen the roots of a cubic equation? Okay, so here are the roots of ax cubed plus bx squared plus cx plus d. So you should have these memorized by next class. No, of course not. If you had to memorize this, of course you'd be upset. What simplifying assumption can you make? To make this a little bit easier to memorize, what can you assume? Without loss of generality, give me a value of A, B, C, or D without loss of generality. With loss of generality, A equals 1. Just divide through by A, as we might as well assume the leading coefficient is 1. You can also adjust things. You can replace x with x minus h, and if you choose h appropriately, you can actually make b equals 0. So as a nice exercise, without loss of generality, you may assume a equals 1 and b equals 0. It's still bad, but it's much better than this. But I can get the 3 roots on a slide. For the next one, I have to shrink things a little bit. And this is just one of the 4 roots. Okay? What can we assume without loss of generality? So without loss of generality, what can we assume? A is 1. And what else? B is 0. So again, that's a nice exercise to prove that it suffices to consider those cases. And if you look at the proof we did of the quadratic formula, we were pulling out factors of A. It seems reasonable that you can do that and just replace C with C over A. Okay. So now I want to try to motivate why we're caring about a lot of these objects. And so one of the things I want to show you is the Riemann zeta function. And so this is one of the most important objects in all of mathematics. And so the zeta function, Greek zeta, is defined as the sum, n goes from 1 to infinity, of 1 over n to the s, where the real part of s is greater than 1. So this converges. So you should have seen this converges in calculus. This is a p series with p greater than 1 converges from calculus. Okay. Do people remember p series from calculus? Okay, so this is the nice thing. This gives us an opportunity to review some things from previous classes. All right. So let's study the sum n goes from 1 to infinity of 1 over n to the p, where p is a positive real. Do we all agree that if p is 0 or negative, the sum is not going to converge? If p is negative, then the terms are going off to infinity. And for a sum to converge, the terms have to be getting smaller in absolute value. So we could use the integral test. And if we use the integral test, the sum n goes from, say, 1 to big N of 1 over n to the p is basically the integral from 1 to big N of, I need a function that equals 1 over n to the p when my input x is an integer n. So I got to figure out what's some function f of x such that f of n equals 1 over n to the p. Any thoughts about what f of x should be? Yeah, almost always what you do is just replace and do a search and replace. Wherever you see an n, put an x. So I have 1 over x to the p dx. So do people remember the integral test from calculus? That, if the sum is monotonically increasing or decreasing, then the sum is basically the integral. The way you can see this is, if I have, a sum of, terms like this, I can bound it, and, here is my upper bound, here would be the lower bound. And I can sandwich the sum between these integrals. And so what does this integral equal? So this is the integral from 1 to n of x to the negative p dx. What does that integral equal? So what function has derivative x to the negative p? Right? We're integrating. What do you do to the exponent when you integrate? We increase by 1. So it's x to the 1 minus p, and then I divide by 1 minus p. And I evaluate this at 1 and n. And this is if p does not equal what? 1. And if p equals 1, then I'm integrating 1 over x. What function has derivative 1 over x? Natural log. But we're adults now, so we write the natural log as log x. Because for us, once you get to college, log is always base e, if p equals 1. And then we evaluate that at 1 and n. And now we can see if p is greater than 1, then the exponent of x is going to be negative, and the sum converges. If p is less than or equal to 1, it diverges. So converges if p is greater than 1, diverges if p is less than 1. So you should hopefully have seen this in Calc 3, or maybe even Calc 2, depending on what they were doing in Calc 2. And this shows you that this sum converges if the exponent is at least 1. It turns out that, zeta of s, which was initially defined as the sum, and goes from 1 to infinity of 1 over n to the s, it turns out this is also the product over primes 1 minus 1 over p to the s inverse, if real part of s is greater than 1. So the proof of this is the fundamental theorem of arithmetic, basically the unique factorization. So primes are the building blocks of numbers. And so, anybody know what year it is? This is not a hard question. 2024, right? We're in March now. It shouldn't be hard to figure out what year it is. What is the next number? What's the next integer after 2024? Yeah, next integer. And the next number after that. Yeah, it's actually pretty easy to write down the integers. There is even a formula that gives you the nth integer. Maybe I'll use I for integer. There's an explicit formula that gives you the nth integer. Does anybody know what the explicit formula is for the nth integer? N, right? We know the integers quite well. In fact, we even know the gaps between adjacent integers. What is the gap between any two adjacent integers? It's just 1. There's really no mystery in the integers. The primes are mysterious. So somehow the primes are connected to this function over the integers. And the hope is that by understanding this function over the integers, which we really do in complex analysis, we can deduce information about the primes. So for example, if we take s equals 1, then, I'll do it this way. If we take the limit as s goes to 1 from above of zeta of s, this is the limit as s goes to 1 from above of 1 over n to the s. This is the sum n goes from 1 to infinity. This is converging to the sum of 1 over n. What series is that? The series has a name, harmonic. And what's true about the harmonic series? It diverges. Therefore, there must be infinitely many primes. Because if there were only finitely many primes, then the product would have to converge when s equals 1. Here's another fun fact. If s equals 2, it turns out zeta of 2, the sum n goes from 1 to infinity of 1 over n squared, it turns out it's pi squared over 6. So pi day is coming up fast. Does anybody know what kind of number pi squared is? So what kind of number is pi squared? Is pi squared an integer? Is it a rational number? It turns out it's irrational. So this is irrational. If only finitely many primes, this is rational. So because pi squared is irrational, there must be infinitely many primes. It's a very strange result. There's a lot more you can say about this. The goal here that I want you to get out of this motivation is that there is a reason why we study something like the sum of the zeta function. It takes what we want to understand, the primes, and associates to the primes this global function defined over the integers. And the hope is that if we can understand properties of this function over the integers, we can then deduce things about the primes. When we're looking at things in number theory, I know there was at least one person who was interested in algebraic number theory. Instead of looking at primes, we might want to look at what about generalizations of primes. And we already know that there are some examples where we don't necessarily have unique factorization. It turns out you can generalize this and you can deduce things about other objects you care about. So part of my goal in abstract algebra is to give you a little bit of a sense of the landscape. What is coming next? What might you see if you continue? Yes?
If primes are integers,
right?
Then 1 minus 1 over prime squared is...
It's rational, right? And in the inverse, correct. But if there were only finitely many primes, a finite product of rationals is rational. But an infinite product of rationals can be irrational. I will quickly prove that. This is the advantage of a small class. All right. An infinite product of rationals can be irrational. So one problem is I need a number that we can all agree is irrational. Okay, so we'll take E. So I want to write it as a product of rationals. And so I want the rational, so I know it's a little bit more than 2 and less than 3. Right? So I can write it as 2. Then I have to multiply by something to make it a little bit larger. Right? What do I need to multiply it by? It doesn't have to be rational. What do I have to multiply 2 by to get it to be E? This isn't hard. You're making it way too hard. What do I multiply 2 by to get E? E over 2, right? I can multiply this by, say, E times 1,000 over 2 times 1,000. Right? And then what I can do is I can take the greatest integer less than or equal to E over 1,000. So I can write this as 2 times the greatest integer of E times 1,000 over 2,000. And now I can put something in here to make it, and I can keep going like this, and I can keep taking, now I'll do 1,000 squared, 1,000 cubed. So this is one way to do this with your number E. So there's lots of games you can play like this. So a finite product of rationals is rational. An infinite product of rationals could be irrational, but an infinite product of rationals could also be rational. So an infinite product of rationals can be rational. And so, so what I want to do now is I want an infinite product, and I want it to come out to be nice. So if I do 1 times 3 over 2 times 2, and then 2 times 4 over 3 times 3. And then 3 times 5 over 4 times 4. And then 4 times 6 over 5 times 5. And 5 times 7 over 6 times 6. Is the pattern clear? Yes? Do we all agree that this is going to be a product of rationals? The 2's and the 3's cancel. The 3's and the 4's cancel. Now over here, the 4's and the 5's cancel. The 5's and the 6's cancel. And so if I just do this, this is going to be up to here. This is going to be 1/2 times 7/6. And so in the limit, what should this equal? 1/2. And so here's an example of an infinite product of rationals that is 1/2. So there's lots of fun games you can play with stuff like this. Okay. So what I want to do now is I want to go and talk a little bit about coding. And so switch to Mathematica. Okay. So hopefully you should be able to see. Yes. Okay. So what I want to do is talk a little bit about, some of the commands that could be of use in what we're doing. Let me try to make the font size a little bit larger. All right. So the first question is how to do things in various environments. So Mathematica likes to use capital letters. GCD does the greatest common divisor. So if you want the greatest common divisor of two numbers, say 14 and 18, what should that be? 2. And it will just return and it will give you 2. What if I do 14 to the 701 and 18 to the 11? What should that be? 2 to the 11. And it will give you that. What if I add 1 now? It did that extremely quickly, right? Can you imagine calculating 14 to the 701? Let's make it a little bit larger. And let's do, 3 to the, I don't know, I'm just typing in a bunch of things, plus 5 minus 56 to the 57 plus 2023. That took almost no time. You can surround something with the word timing, and it will tell you how long it took. Basically, it's so fast, it's telling you it did not take me any time to do this. This was not a challenge to me. Right? If you have to calculate GCDs, which you may on one of the homework problems this week, here's a great way to do this. You can use Wolfram Alpha online. I'm not going to go. So you can go to Wolfram Alpha online to do a lot of this. Mathematica is more powerful if you run it in your command line, but there's a lot of things you can do online. So if you want to work with matrices, the way you define a matrix, so I'm trying to keep the font size large. Let's let M be a matrix. So you surround it in curly braces, and then you do row by row by row. So do you want to do a 2 by 2 or 3 by 3 matrix? 2 by 2. So we'll do M is 1, 2, 3, 4. And a semicolon means, suppress the output when you run the line. So if I hit Shift Enter to compile, it suppresses the output. If I do Shift Enter without the semicolon, it displays it. How many of you have seen the movie The Matrix? Anybody seen them? All right. Let's get that joke then. When you look at this, does this look like a matrix to you? So there's a command called matrix form. You put M in that, and then it displays it as a matrix to make it easier for you to look at. So I'll let M be this matrix, and I'll let A be the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. I might have mentioned this matrix earlier in the semester. Have I mentioned this matrix A? Okay. What is the determinant of A? So the first row plus the second row is twice the middle. So once you have the matrix 1 to n squared, once n is at least 2, all the determinants vanish. So what's nice is I can quickly calculate a bunch of things. What might be something you might want to know about a matrix? Determinant. So I type DET determinant of the matrix, and I get the determinant. What else might you want to know about a matrix? Maybe you might want to know its trace. So this is garbage. It basically says trace is not the correct command in Mathematica. So I can do maybe question mark means help, look up, and I'll look up trace. So trace generates a list of all expressions. So I hit this bottom arrow. Do I want to look locally or do I want to look on the web? I'll look locally. And so it gives me a lot of help. When I was young, you did not have stuff like this in programs. You actually had to have reference books. Now everything is online or in the program. So when I start looking at this, I very quickly see this is not what I want. So I could try over here in the help line, just typing the word trace and see what happens. So trace, trace on, trace def, trace original, trace print. None of that seems to be helping. I can go on to next. Oh, TR is the trace of a matrix. Okay, so that was enough to find it. I could also, instead of doing this, maybe I could type in here, not trace, but maybe matrix. Matrix is unknown, matrices. Okay, so I now click on over here to expand. What does it know? I'll look locally, not on the web, and it opens up this So this represents the domain. Okay, so I've got all these different things. Oh, examples. Okay, examples are often useful. Scope, applications, properties, other things over here. I can start looking to see, is there anything useful? The properties and relations. Yeah, it's what other things do I have related to it? I have matrix Q, tensor array, dimensions. So this is not as directly useful. And so sometimes it takes a while to figure out what to find. If you're not sure what to do, we could put up over here, and we saw that when we searched for trace, we did get on the second page. What else could you do if you wanted to figure out how to take the trace of a matrix and you couldn't find it easily? Google it. Just go to Google or your favorite web browser and type in, how do I find the trace of a matrix in Mathematica? And it will punch up the answer very easily. So what is the trace of a matrix? It's the sum of the diagonal elements. So if I do trace of A and trace of M, I get 15 and 5. Can I multiply A and M? No, they're wrong dimensions. So the way you do matrix multiplication is you use a dot, A dot M. And it says they have incompatible shapes. All right, so I need another matrix that's similar to M. I can't use N because N in Mathematica stands for numeric. So I will use M and I'll use W. And so I'll let W be the matrix, I don't know, 2, 3, 5, 7. Okay. And now if I do M dot W, it can do that. Whoops. Yeah. So it didn't compute that. The reason it didn't compute it is I added W here, but I never recompiled these lines. So I have to click on these lines and do Shift Enter. And now do you see how W is no longer blue? It was blue a moment ago. So for instance, if I use a new letter, if I use Q, Q is in blue. If I use B, B is in blue. It's something new. When I turn it to W, it's now been compiled. Okay. So now if I do M dot W, I get the following. What do you think I might want to compare M times W to? I have a product of M and W. What might I want to compare that to? W times M. And so I could do W times M, and I can clearly see that these are not the same. I could, of course, surround these with matrix form. And you'll see much clearer. I could even subtract one from the other and see that it's not the zero matrix. Here, it's displaying them as two matrices. So if I want to subtract them and then put it in matrix form, then that's going to give me that. What is the determinant of a product? Product of the determinants. And so you can test that over here. I can look at determinant of M dot W minus the determinant of M, determinant of W. Is the determinant of a product the product of the determinants? Well, that works for this specific matrix. So let's take some new matrices. Let's let Q1 be the matrix A, B, and then CD. And let's let Q2 be the matrix W, X, Y, and Z. What should the determinant of Q1, Q2 minus the determinant of Q1, determinant of Q2. What should that equal? It should equal 0. Is that 0? It might be. So how would you show if this is 0? What would you have to do? It is 0. How did you do that? What's the word you used? Simplify, FOIL. Mathematica has a simplify function. Just surround that with the word simplify and tell Mathematica, can you simplify this for me? Yes, it's 0. Now, this was not that bad of an expression. You were able to see in your head that it's simplified to 0, but this is the power of using something like this when you're doing calculations. If I want to do a permutation matrix, we talked about permutations. Maybe I'll let P1 be the permutation 1, 0, 0, 0, 0, 1. Oh no, let's do 0, 0, 1, 0, 1, 0, 0, 0, 0, 0. Where do I need to have the 0? I think in the second spot, 0, 1, 0, 0. Oh no, I have two things in the first component. So this one should be a 0 and I'll make this one a 1. Okay, so this is a permutation matrix. So we talked a little bit about permutations. So this is going to switch around certain elements. Which elements does this switch around? I'm sorry? Everything but the first. So it takes the first one and keeps it as the first one. It takes whatever was in the second spot and moves that to the fourth spot. What was in the third spot moves to the second spot, and so on and so on. So we talked about permutations and stuff like this. If I have a finite group, some power has to be the identity matrix, right? It's got to wrap around to the identity, right? So let's do a little for statement. So for n equals 1, n less than equal to 10, n plus plus. So this means add 1 to n. Print my number is n equals n. Okay, this is just a simple program to show you how we can do a for statement. Okay, well, rather than just printing my number as n, let's do something a little bit more interesting. For n equals 1, n less than equal to 10, n plus plus, let's print matrix form of P1 to the n. I think that will work. Nope, it's not working. So what do we get for all of these? It's the same matrix every single time. So I think the command is power. So what I sometimes do is I sometimes have a second notebook over where I can just test things. So maybe matrix power, yeah. Matrix power mn gives the nth power of the matrix M. Okay. So I can't just define it like this. So I'd have to do matrix power of my matrix P1 to the nth power. And now you can see things are starting to change. And we do get the identity matrix. When you're looking at this, it's kind of hard to tell which power this was. So let's make it a little bit nicer. We're going to print, let's print, n equals, and then we're going to print n. And P1 to the n is, and so now it just prints it out a little bit nicer. If we wanted to, I could even go one further and have it, print out like this. And so now it'll even print out the power like that. If n equals 1, and p1 to the 1 is this, p2 goes this. And so we can see that there is a power of this matrix that gives us the identity. So you give me, various matrices, I can try to figure out, do they have a power? One of the homework problems was talking about, finding out if certain groups are cyclic. Let's take a prime that wasn't on the homework. So you've, of course, all started the homework by now, and you've all looked at the problems. So let's take a large prime. So anybody know what the next prime is after 2024? Or at least what the next prime is not. It's not 2025. So let's do the next prime command, 2024. So the next prime after 2024 is 2027. So we don't have to wait too long. So the question is, let's consider the group Z mod 2027Z. Let's look at the invertible elements mod 2027. So this is Z mod 2027Z star. Is this cyclic? So one of the homework problems was to look at whether or not certain things are cyclic. So 2027 is going to be a little bit large, right? So it could take a while if I gave you this to do by hand, right? If you would try to show it's cyclic, you have to find some element such that its powers generate this. What number would you try first? 2. And if 2 works, you're done. And if 2 doesn't work, what would you try next? And if 3 works, you're done. If not, you try. So you could try 4, but 2 doesn't work. So if 2 doesn't work, 4 can't work. So I'm saying we're trying to find a generator of the cyclic group or show that nothing exists. So 4 is a power of 2. So if 4 doesn't work, no power of 4 could work. So we try 5. If 5 doesn't work, what would we try next? So if 5 doesn't work, what would we try next? Why not 6? It's a product of them. It's not a power, but so it's possible. Maybe you can prove that if 2 and 3 don't work, 6 doesn't work. But 6 is at least a possibility to try. So let's talk about how we would write some code to investigate this. Okay, so I'm going to create a program. Finding cyclic generator. Okay, this should hopefully be a good name. So I'm going to do p underscore. So the underscore means that this is a variable. Module means I'm writing a program. And one of the things that's nice about Mathematica is it immediately, when you start a bracket, it puts in another bracket to close things, so you're not missing something. I'm a little bit lazy. Over here, the 2 curly braces means I have no local variables. These are no variables that live just within this function that I'm creating. Okay? Sometimes when you're writing code, it's better not to code efficiently. So do we agree that 4 cannot be a generator if 2 is not a generator? But it might be easier to just write the program to check 4. So what are my possible candidates? What do I have to check? For g equals 1, g less than equal to, I'm sorry? But now I'm using p. So what's the largest g could be? No. We go all the way up to p minus 1. I know that p minus 1 is not going to be the generator, but I look at all the elements from 1 to p minus 1. These are all my potential generators, G++. And then the curly braces means, this begins the for loop. Begins the for loop. This is a comment. And over here, this ends the for loop. So the curly brace is begin, the other curly brace is an end. And the G++ means increases G by 1. So we're going to count from 1 to G, and we're going to see if it is a generator. Okay. So what would it mean for G to be a generator for Z mod PZ star? So what would it mean to be a generator? It generates the whole group. So the first time we get the identity should be when we raise it to what power? Hello? Yes, I'm in class now. If this is not an emergency, can I call you back? Okay. Just with my job, I have to always take calls. So how do we agree that if it's a generator that the first time we get the identity is p minus 1? So what we can do is the following. So we take a G, and G can go from 1 to p minus 1. And then what we're going to do is for, let's say, power equals 1, power less than equal to p minus 1, power plus plus. If now we're going to look at G to the power, if that equals 1, it's not a generator. Right? We know if we raise it to the p minus 1, it's going to be equal to 1. This is whose theorem? So I'm sorry? Fermat or Lagrange, either one works. So I know if I raise anything to the p minus 1 mod p, I'm going to get 1. So let's look and raise it to a power less than p minus 1. If it ever equals 1, then G is not a generator. Right? So let's start off right now with G generator equals 1. So use 1 for generator, 0 for not generator. So when I look at G to the power, it doesn't have to equal 1. What does it have to equal? So it's close to 1. Mod what? So we want mod G to the power mod what? P. So this is telling us raise G to the power. If it equals 1 and the power is less than p minus 2, then we'll set G generator equals to 0. And that means we found something that's not a generator. Let's make sure we have mod correct. What should the mod of 17 mod 4 equal? Well, 17 mod 4 is 1, and we get 1. What's the mod of 4 mod 17. That should just be 4. So this is just making sure I have things in the correct order. What command do I use to look up something in Mathematica? Use a question mark. So I could do question mark mod, and it says mod mn gives the remainder of m by n. So I'm using mod correctly. So if I look at this, the generator test, it will set the generator equal to 0. And I might need one more bracket to close things off. Right, so that closes off the if statement, and then that closes off the for statement. It's just, okay, it just accidentally identified more than one. All right, so now I can test and see if G is a generator. If G generator equals, we use a double sign for the equals for comparisons, equals 1, then we're going to print, found a generator. It is, and then we'll just say what the generator is, and that'll just be G. If the generator is not 1, then it failed the test, and we move on to the next number. So does everyone see how we just keep looping through this? I start off with a value of G. I take G equals 1, 2, 3. Is there really any need to start off with G equals 1? No. So we'll start off with 2. This is going to be a way to keep track. I'll set the generator to be 1 as a default. So I'm going to assume right now that G is a generator. And now I do my test. I see if a smaller power fails. And if a smaller power fails, then I reset the generator flag to be 0, and I'm done. So let's see if this works. Instead of using 2027, can somebody give me a smaller prime to try? $11. So we found some generators, 2, 6, 7, and 8. So we can check and see. For n equals 1, n less than equal to 10, n plus plus, print a to the n. Let's do this mod 11. And here, oops. Let's set a to be 2. And did we get 1 earlier than the 10th thing? Or was the very first time we got 1 when we took it to the 10th power? Yeah, so that shows it works for 2. What should we try next? 6 is legitimate. And was that the first time we got 1? There was something else you could have tried after 2 and before 6. 3. So 3 should not be a generator, and we see that we got a 1 earlier. 4 should not work. If we try 8, that should work. And so this is at least giving us some confidence that this might be working, that we might have actually found some code. And so there's more than one generator. We found that there were 4 generators for 11. So instead of 11, we could do, maybe P equals 11 here. And by coding it like this, do you see how this gives us greater flexibility? Yes? And so again, what I'm trying to do today is just show you how you can do some simple coding to investigate a lot of things in this class. And now if instead of using the prime 11, give me another prime. Let's do maybe 19. And so we have some generators, 2, 3, 10, 13. Maybe 2 is always a generator. Would you be willing to make that gamble? It's been a generator twice. All right, so instead of 19, give me another prime. Let's try 20. No, 7 was homework. Let's do 23. All right, so it doesn't work for 23. So now if I want to test things for 23, I would have to change the P to 23. I would change the 8 to a 5, and I would go down and I would see that it works. And that the first time I get 1 is at the very end. I could make this a new function. I could call this generator test and have A and P underscore as my inputs. And now I have a function. And so whenever you're using something multiple times, you want to make it a function. So I'll do 20, 23, and that tests and I see, yes, it works. All right, so what do you think? Should we try this with 2027? Do you think this is going to take a while to run? So I'm going to do a timing, so we'll get a sense of how long it takes. So it is going and it is finding a lot of generators. Boy, is it finding a lot of generators. It's just killing my notebook right now. And it's still going. It's only in the 900s. So there's a lot of generators. If I do Alt period, that should stop the calculation. Yeah, that stopped the calculation. So this wasn't too bad. One of the things we could do is we could have a special thing. Do you want to find all the generators or just one generator? Maybe you want to give yourself some options.
Like the biggest one.
The biggest or the smallest.
Oh, if the smallest, we'll just stop at the very beginning.
Right.
But we want to test how fast it is.
So again, what I'm going to do is I'm going to add to just one. So I'm going to put some notes here. If just one equals 1, stop once we find a generator, otherwise find all. And so now, if the generator equals 1, we found a generator. If generator equals 1, how can I stop the program if we found a generator? So how would I do that? So what I'll do is I'll make this into I'll do this 2 statements right now. If G generator equals 1 and just 1 equals 1, then we'll stop. So now if I try to run this program, I shouldn't have done that. I'm sorry?
Where are we assigning values?
That should be an input. It shouldn't have compiled. So if I put in a 1 here, it should stop now after it found a generator. And so now what I can do is I can do next prime after basically the next prime after 200,000. And we can see this is taking it a while. Almost a whole second. And 2 worked. Now, I'll go a little bit further down. And again, this should show you the advantage of being able to do some simple coding. So now, it hasn't found something yet. This has definitely been more than a second. I'm getting worried. So the code that we have is actually very inefficient. And the reason is, once we find a power such that g to that power is 1, we know that can't be a generator. Why are we checking more powers? right? This is incredibly, so this took me 21 seconds to find that it was 3. And the reason it took so long is once it found that 2 was not a generator, it kept checking powers of 2. So we could make this more efficient. If this equals 1, then let's do 2 things. Oops. So we're going to do 2 things now. We're going to make the generator equal to 0. So that's going to tell us that it's not. And now we want to break this loop. So how do we break this loop? We don't want to keep checking more powers. Power equals P. And again, I'm just going to put it the +1 to be really well above. So now it took us 21 seconds before. Now let's see how long it takes. So now I'm going to break the loop as soon as I find that 2 doesn't work. I'm going to move on to the next. And so hopefully this will take less than 21 seconds, and we'll see that there was some gain in this. I'm actually surprised that it hasn't broken by now. I believe it's because, yeah. So let's see, did we do this correctly? So if the power is, okay, so it did save some time. And again, the bigger things are, the better it is. The next thing you could do to try to make it even better is, this is a little bit inefficient. You're calculating G to a power. Because what I'm constantly doing then is I have to raise G all the way to the power. Whereas what I'm really doing is I'm just multiplying by G mod P. And so if I store the result of it before and then just multiply that by G and then mod P, that's going to be a lot faster than from the beginning going every single time. So whenever you have something like this, it's always dangerous to modify the code when something works. Always save your files. So I'm going to make this called efficiently finding the cyclic generator. And so now what we want to do is we'll do maybe start equals 1. For power goes from 1, et cetera, et cetera, et cetera. So what we should do is we're going to start off with the second power, and we're going to take the current value. Let's make the current value 1. And so how do we change the current value? What should the current value be? So I've got to make the for statement a little bit bigger. So my new current value should equal the old current value times what? Times G. But I only want to care about this what? Mod P. So that's my new value. And so this should be G to the power mod P. Right? And so now I just look at, is current, when I divide by P, is that equal to 1? Do I need to actually look at this mod P? No, because I've already modded P before. Don't do any calculations you don't need to. Save as much time as possible. So let's see if this works. Efficiently cyclic power. And what was the number we were using before? Yep, so let's just put that in as a fair comparison. Boom! Look at the change in time. The timing was 0.1 seconds. Before, the timing was 18 seconds. So this is the power of learning how to write simple code. You can explore a lot more things very quickly. You can gather data, you can make conjectures, you can explore things. This is a skill you really want to have as a 21st century, mathematician. This is going to give you marketable skills. And so over here, theoretically, is there anything wrong with the first code? No, but it's inefficient. It's constantly doing a lot of calculations we don't need to keep doing. Think of the fast multiplication we did when we talked about RSA. Faster ways to evaluate things. It makes no sense to keep calculating G from the very beginning, keep raising it to higher and higher powers. Store what you did and modify that. So again, a lot of what I want you to get out of this class is good ways to attack problems. Theoretically, there's no problem with the first code, but from an application standpoint, it's terribly inefficient. Do you think I can put in another 0 and have this work? Yeah, let's see. Found a generator. Now, of course, if 2 is the generator, it's going to find it somewhat quickly, but it still has to go through all the possible powers. So I'll put in another 9, and hopefully, 2 won't be a generator, and we'll see, how long does it take? It's still 2. So, then the question becomes just, how often is 2 going to be a generator? And, this is a very famous conjecture. I think it's by Artin. And so, we'll try another one. It's 7. So this means 2 failed, 3 failed. The code actually checked 4 because it would take me more time to program it, I think, not to check 4. But if we really were, running this for many things that we cared about, then you would put something like that in. So in less than 3 seconds, and it's probably worth knowing just how big is this number. What is this prime number that we're looking at? 2,008,003. And we found a generator in less than 3 seconds. So this hopefully gives you a sense of just how we can use programs like this. I don't expect you to become master programmers, but I want you to be a little bit aware of what's out there because this is worth knowing. All right, so this is a good place to stop. Then this section will have the theory lecture on Thursday. Okay, so let me switch back over here.